So yeah, as Marco said, today I'm going to be talking about some of our latest work on architecting next generation autonomous vehicle autonomy stacks. And here, we're really focusing on developing the next generation of AV autonomy stacks. And to understand why we need a next generation, let's talk a little about what the classical architecture for autonomy stacks look like. So typically, they look something like this. They're very highly modular, and you typically have key components for detection, tracking, prediction, planning, and control. And this is the typical structure that's taught, for example, to students here or around at other universities, and that many AV companies adopt. So some key advantages here are that you can interpret what these modules are outputting. You can develop them independently. However, there are information bottlenecks between each of these components. So you might have a performance ceiling based on the information that you can actually pass from upstream to downstream. Now, on the other hand, kind of a recent advancement has also been looking at end-to-end architectures, where typically you're trying to connect perception directly to control through like a neural network or a few neural networks. And you're only really implicitly encoding key capabilities like agent prediction or detection or tracking. Now, some key advantages are that you might actually have a higher performance ceiling because now there's no information bottlenecks. However, you also don't know if you can guarantee safety because you typically can't analyze, are you detecting all the objects? Are you able to track them through time? Are you able to actually safely avoid them? There are some difficulties about making formal safety claims as compared to maybe modular autonomy stacks. So given the current state of things, a natural question is whether we can maybe design something that takes the best of both worlds without maybe having too much of the detriments. And in particular, if we view these architectures on a spectrum, what would something in the middle look like? And so this is actually part of what I'll talk about today, which is I'll be going over some of our latest work on designing modular and differentiable autonomy stacks, which combine the reusability and interpretability of the modular AV stack, but also with the theoretical higher performance ceiling of end-to-end AV architectures. Now, the other necessary innovation in order to actually develop newer architectures like this is in the surrounding infrastructure. So in particular, I'll also talk later in the talk about some of our latest work on simulation, leveraging data for better behavior, and I'll show some of our really latest work that we just submitted a couple weeks ago in this direction as well. So this is actually exactly what I'll talk about today. So I'll first talk about some methods for how to expand the flow of information between these stacks and the modules in the autonomy stack. I'll talk about how we can optimize some components directly for downstream performance because of enabling modular differentiability. And then lastly, I'll talk about leveraging data for simulation and some of our latest work on generating realistic human-like traffic. So without further ado, I want to focus the first part here on talking about how we can combine three typically learned modules, detection, tracking, and prediction, to enable better performance. So typically, when we want to remove information bottlenecks in the AV stack, it very quickly becomes a question of robustness, because all of these components produce uncertainty, or at least they're not going to be perfect. You're going to have errors. You're going to have something that you need to take into account. And so there are many sources in the uncertainty stack. And the running example I'm going to show here first is in detection, where you might have probabilities about what class an object is, or you might have uncertainty about where it's located in the image. And I guess it's hard maybe to see if you're sitting here, but there's kind of a lot of these probabilities, they fluctuate, and you have these kind of classes that switch over time. But as you can imagine, this uncertainty is going to affect tracking, which is going to affect prediction, which is going to affect planning, which is going to affect how your vehicle moves in the world. And so all of this is actually really interconnected, whether you want it to be or not. And so, our group has done quite a lot of work in trying to analyze some of this uncertainty and explicitly incorporate it in different modules here in the stack. But today in particular, I'm going to focus on this connection between tracking and prediction. And I'm going to focus on how we can make prediction models that are robust to the kinds of errors that you typically see in tracking. And in particular, I'll talk about the most common kinds, which are fragmentation and ID switching. And I'll show some examples of what those look like. So in this video, we can see what some of the tracking errors look like in the wild, where basically an ID switch is kind of like if you have two vehicles in the real world that maybe come very close to each other, or they kind of one obscures the other, then your tracking system might think, okay, these two vehicles, they didn't just continue straight past each other, they turned around and went like this. Because again, they look maybe the same, they're passing in front of each other, they're very close. It's very easy to get confused. Another kind of problem is called fragmentation, where you have, let's say again, another vehicle passing in front of the other, and you say, okay, the vehicle that was occluded, it's now not the same vehicle that you observe later. You just say, you give it a new ID because, hey, I saw one vehicle, then I didn't see anything, and then I saw another vehicle. And so this is typically called fragmentation. So these two problems are very common in multi-object tracking. And it's not just that they're common in tracking, they're extraordinarily detrimental in prediction. Because in prediction, you really rely on these tracked trajectories to develop an understanding of dynamics, of motion of these objects. So to give an illustration here, on the top left, we have an object that was tracked perfectly. It's a car that's turning left, and we can see that the resulting yellow predictions, they're more or less reasonable, right? They're continuing towards the left, they're kind of staying on the road. I know it's tough to see that this is a road here, because I'm kind of visualizing the LiDAR outputs, but that's my bad. But you can see that the predictions look reasonable. When we have a tracking error here, and we have an ID switch, you can see that now we have, let's say, like a false positive detection that causes your bounding, your tracker to think, this vehicle now moved up suddenly. It has like an errant acceleration. And as you can see, the predictions are now off the screen, right? They're useless. And actually, when you evaluate this quantitatively over like an autonomous driving data set, you can see that these kinds of tracking errors, they significantly increase the presence of prediction errors. And they can really make your lovely predictor that you train on ground truth data completely unusable in the real world with errors that are so high. So to remedy this, what we asked in the group was, okay, the hard part here is that tracking typically needs to make a hard decision of which detection is mapped to which previous track. And the question we had was, okay, this hard choice really loses a lot of data because there could be a lot of uncertainty that you just have to say, okay, if it's 51%, 49%, I just have to take the 51%, and you're neglecting all of this uncertainty. So we asked, okay, can we remove these hard associations that need to be made, and can we instead pass all of this information to your downstream predictor, which I here draw as like a transformer-based model. So this is actually the exact idea that we evaluated. And rather than just directly taking all the previous detections, we took the previous detections as well as their similarities over time. So when I say here similarity, I mean, for example, visual similarity, or the how close they are in frame by frame in space. And these, how similar an object is from frame to frame, we call that affinity. This is a term that you might hear in computer vision a lot. And so we take this affinity information as well and directly structure it inside the transformer's attention, where we're trying to attend, one time step, like one set of objects in one frame to sets of objects in previous frames. And when we take this soft information now, rather than making a hard choice, we can actually reduce the presence of prediction errors in these cases where there are tracking errors by, up to 80% here. So now finally we can actually start to harness some of this uncertainty and not get demolished when we have these errors. And to show an example of what this looks like, on the left here I have the standard pipeline where you have a decomposed system of tracking and then prediction. And what you can see is these are all parked cars here, but you can see that when there's like this errant associations, there's like predictions that are being made for these parked vehicles to move, which is problematic if you're going to try and pass next to them. Whereas on the right, with these same detection errors, we don't have any of these same predictions being made. We don't have any of these errant predictions for parked cars.
So when you say you changed it from a hard decision to a soft decision, essentially what you did is you had the model implicitly figure out how to track.
Exactly correct. That's exactly correct. Yeah. In case the question wasn't heard, by switching from hard decision to soft decision, it's basically tasking the model with doing tracking implicitly under the hood. Perfect. So moving on, looking a little bit more downstream, the next thing that we wanted to look at was, so okay, maybe this wasn't so surprising, right? Because at least detection, tracking, and prediction, a lot of those are learned components. So it's actually very easy to connect things without maybe losing too much information. I know tracking wasn't learned here, but we found a nice way to kind of bypass it and have the model implicitly encoded. What about when we look downstream at prediction, planning, and control, which typically have a mixture of learning-based components and handcrafted components? And traditionally here, prediction, for example, is typically a neural network. So I'm going to go with a running example of some specific prediction network, but typically it's learning-based. And then we have a planner and a controller, which are typically handcrafted, hand-designed, hand-engineered for, let's say the specific vehicle that you want to control or the specific design domain that you have in mind. And so the question here is, how can we actually combine these and maybe enable differentiability throughout all of these modules so that the actual final goal of driving behavior can influence how the prediction model learns? So in a traditional system, typically the only component that's learned is your prediction model. And your prediction model is tasked with estimating what will happen in the future for all the agents around you. And then you use that information in a planner. So in this running example, the planner that we use is a very simple sampling-based planner. You sample some amount of candidates, and then you evaluate them using a cost function, taking into account your predictions. So you could say, OK, I want to sample the one that has the lowest chance of colliding, as an example. And then you'll take the lowest cost plan, you'll pass that into a controller, it'll apply a little bit of dynamic smoothing, and then you can just drive on it. So this is like a very simple but typical prediction planning control stack. What we wanted to look at in this work was making those two end components differentiable. And in particular, the way that we did this was, for the controller, we used prior work. There exists quite a lot of work on making MPC and other optimization algorithms like it differentiable. And then we also made that simple sampling-based planning algorithm differentiable by switching it from just ranking these kind of sample trajectories by a cost function, and we changed it to more like a classification algorithm where you still have these sample trajectories, but now you have a model that's kind of classifying which of these is most likely to be the best. Because then at least now you have that differentiability in mind, rather than having to pick like an argmax or an argmin, I guess in this case, which is non-differentiable for planning. And so the key thing here, like I said, the key thing here, connecting us back to our original goal, was to enable downstream task losses and gradients to propagate all the way through these modules and inform how we train our prediction module, or at least prediction and maybe anything upstream. And so the way that we trained our model was basically, we have some data set that we're using, like some public open source autonomous vehicle data set. And what we do is we add costs for each of these components to train them. Like we need to train that classification module in the planner. We don't have to train anything in the controller, but we at least can evaluate the overall performance of the output trajectory by computing like a hindsight cost. So hindsight cost here basically means how different is the control that you enacted compared to if you had perfect knowledge of the world. So at least you have a sense of maybe what the best possible performance is compared to what you did. And that's kind of what we use as like downstream final performance measurement. And then basically, we trained these different components. And then, so we kind of trained each of them separately. And then we had a final round of passing all the gradients through and training each of the modules all together. And what we found was that compared to the traditional stack where you have the decomposed system, what's funny is actually the prediction performance was more or less the same. So in terms of like the actual, if you just measure the prediction output, nothing really changed, but the planning performance significantly improved. And what this basically means, and so here the hindsight reward is basically how close are you to optimal? So to that perfect trajectory if you had perfect information. So here the plan with our differentiable stack was 83% of the reward of the this perfect plan, or at least the all-knowing plan, whereas the other standard module stack was only 71% of the way there. And so what you're able to see here is that although the kind of average accuracy of the predictor didn't change at all, where it made errors did change. So now what we were able to do was basically learn a prediction module that was more useful for planning. So rather than just making kind of uniformly distributed errors all across the scene, it learned, for example, to care a little bit less about objects that are 80 meters away, or a little bit less about objects that are, turning completely away from us that will never be able to, turn back and influence the ego vehicle's behavior. I see a question back there.
How do you know that it was that the places where the errors changed, like that's the reason why you saw it? Planning, could it also be just that the planner, like the calibration between the predictions and the planner, they kind of match because you're training both of them in parallel?
Yeah, it's a good question. So the first thing is we visualize. We have like visualization, so that helps. But actually, the second thing you said is also an important point. Maybe the calibration is better. Like maybe the uncertainties are better. I don't have numbers for you. So I don't have like I can say one thing definitively, but at least towards such an approach like this, I think that's only a benefit if you can actually align the output of uncertainty with the use of uncertainty. Yeah, thank you for the question. Are there any other questions before I move on to the topic of evaluation and simulation? Perfect. So the final broad topic that I'll discuss is, let's say that we have a fantastic stack and it's differentiable and modular and whatever, it's perfect, and we're really happy. How can we actually be certain that this thing is really as good as we think it is before we actually want to deploy it in the real world, where it kind of matters how good your plans are? So, simulation is in many ways the holy grail to scaling up the verification and validation of autonomy stacks. And indeed, in the past few decades, we've seen the autonomous vehicle research community has made tremendous progress in developing tons of simulators with very strong, earlier on it was very strong dynamic and kinematic modeling performance, but now we have simulators that can photorealistically render an environment. And really, so you can now even test your perception stack as well in the mix. However, even with all these fantastic simulators, it's still difficult to actually just directly apply them to the task that we have at hand of really fully evaluating an autonomy stack. And that's because arguably the key missing piece is that the behaviors of other simulated agents, such as cars and pedestrians in urban environments, are still controlled by very simple logic or very simple, differentiable, what's it called? Differential equation type model, like state space models. But unfortunately, real-world driving behaviors are much more complex than these simple models. And so to truly create a realistic driving simulation where you can actually harness all of these photorealistic elements, we need to build intelligent agents as well so that we can generate realistic human-like driving behaviors around the ego vehicle. So concretely, we've identified here 4 key desiderata for simulation, for traffic models to be useful for simulation. So the first is probably obviously fidelity, which is, can we actually synthesize agent behaviors that are realistic and faithful to how humans drive in the real world? Diversity, can we generate a wide range of realistic traffic behaviors? Because it's not just, if you're at an intersection, there's not just one way that traffic could move through that intersection or through the, whatever environment. There's multiple possible ways that are, more or less equally likely. The third is controllability. So we don't just want to generate tons of very, varying types of scenarios. We want to actually steer these simulations to the kinds of scenarios we care about. Maybe we want to specifically evaluate a left turn or an unpredicted left turn or some kind of strange right turn scenario with weird road dynamics, weird road geometry. So we actually need to be able to also steer these models to give us behaviors that we're particularly looking for. And then lastly is a bit more of a broader goal of adaptivity. So typically a lot of the models that we'll be training to do, to generate realistic behaviors, we'll be training them from specific data sets that were captured in, take your pick of cities in the US or around the world. The problem is, the whole promise of simulation is that we can simulate anything, or theoretically we want to simulate anything. And so if I have a model that's trained in data from Boston, New York City, Singapore, or whatever, what happens when I move it now to San Francisco, or Seattle, or Toronto, or whatever, right? We need to be able to actually adapt these models to new regions, and hopefully without having to collect a ton of data or do a ton of hand-engineered fine-tuning, because that's not really scalable. Now, along the way, we'll talk about some of the challenges that you run into and maybe some ways to solve them. But the first typical challenge is stability. So how do you actually prevent your simulation from leaving nice, smooth driving behaviors? And this typically happens when you have longer horizon simulations, where maybe you've trained your models to only predict motion for, I don't know, at most 5 or 10 seconds. But now you're simulating for potentially a minute or longer, if some scenario is needed. So we'll talk about some of these challenges as we get to them. But I want to start, and also, unfortunately, due to lack of time, I won't talk about adaptivity today, but we do have work on this, so by all means, check out some of the links I'll put up at the end, and you'll see some of our work there. Now, as I've shown in some of the previous slides, we definitely have the capability to model human behavior, because we're learning it in the car to predict the motion of other vehicles. So why don't we just try and use some of these already quite strong and quite accurate behavior models in order to simulate agents for us? So the question here is, can we just do this and problem solved, and we're all really happy? Unfortunately, no. And I'll show an example of what that looks like. So on the left here, I just have a normal driving trajectory that's taken from just logged data. So this is very smooth driving motion. As you can see, cars are just typically sticking to the lane, and the orange car here is like the agent that's being modeled, let's say. So this is ground truth data. If I just take out even a state-of-the-art prediction model and I apply it to control this vehicle in an autoregressive fashion by making some predictions, driving for a bit, feeding that new data back in, and repeatedly doing this, as you can see, very quickly this prediction model gets out of it gets out of normal driving behavior, and it's basically useless, right? It's just stopping here in the middle of the road. And the fundamental reason behind this kind of divergence from good behavior lies in the fact that prediction model errors accumulate over time. And when they accumulate enough, now your neural network is kind of outside of the training data distribution that it was originally trained for. And neural networks have quite a difficult time, even with all the amazing methods that have been developed since. That's still a very difficult problem. And so, unfortunately, you make a bit of error at the first time step, then you feed that back into the model, make an error on the next time step, and then it just grows, and it's hopeless, as you've seen. So the first of our works in this direction was actually targeted to tackling this problem. So the way that we tackled this problem is that we decomposed the problem of behavior modeling for simulation into 2 subproblems. The first is predicting where the agent wants to go. And then once we have kind of like a goal point in mind, the second subproblem is basically connecting A to B and having connecting where the agent is currently to where it wants to go through this inferred goal. And the video I'm showing here, which I'll play again. So what you can see here on the right is that first level of the hierarchy where we're estimating the goal of where the agent wants to go using this kind of spatial probability heat map over the scene. And then on the left, you can see the resulting, like the trajectory that connects the two. But you can also see that even when we're repeatedly running this, we actually have very stable driving behavior that you can actually just run, for a while. And most importantly, this modeling of this agent happens. It's like every agent is modeled independently. And what's good about this is every agent actually can think for itself. And it has kind of like an observation neighborhood around itself as well. So you can actually get very complicated behaviors even from a simple model like this, which is just kind of estimating a very likely place for this agent to go without really much prior information. And even better, because this model that we've developed, specifically it's called bits, this model that we developed also has stochasticity inside it. So we can actually even from the exact same initialization of the scenario, we can generate diverse rollouts for even the exact same map. And this is a really good thing because it enables counterfactual reasoning, or also known as what-if reasoning. Now, I've shown you some nice GIFs here, but that's, all of that's really nice, but is it actually, how can we actually evaluate that these trajectories are indeed good? And this is quite a difficult question because it's very difficult to evaluate behavioral realism, especially when you don't have an associated ground truth trajectory that you can compare to. Remember, the whole point of simulation is that I want to generate new and diverse and not, realistic, but not necessarily seen before trajectories. And so you can't really compare that to, just ground truth data that you collected. And so the way that we tackled this problem in this paper and in some of our follow-on simulation works is to basically come up with a concert of metrics that kind of help you pinpoint what are the strengths and weaknesses of different simulation approaches. And there's kind of three different levels to these metrics. So the first is analyzing the specific trajectory level, like trajectory level information that is output by your simulation model. So here, what you can look at is, for example, over repeated simulations, how much area is covered by your motion? How diverse are the trajectories that are generated per rollout? And what are the failure rates? So here I mean, for example, collision rate or driving off road. So at least we have some semblance of following rules. The second level is that you can kind of step back a little bit and look at statistical differences to real world data. So maybe I can't compare exactly on a trajectory per trajectory basis, but what I can do is I can compare kind of the general distribution of some of the dynamic quantities that were output by the model. So I can look, for example, at the difference in the histogram of speed or jerk or acceleration or whatever else quantity that you care about and compare that to real world collected data sets. And then lastly, and this is probably a little bit in the researchy space, is maybe I can try and learn a separate model that's just focused on devising a measure of human likeness or human likelihood of the kinds of trajectories that you're generating. It's a bit weird though because you're using one model to evaluate the other. So I'm going to say definitely still more work needs to be done on this space, but there are some ideas here, and you'll see some research works that are doing this. Now, I already so far talked about fidelity and diversity. The third desiderata was controllability. So one thing, is it's one thing to generate nice behaviors, but the other thing is how can we actually generate the specific behaviors that we care about? And so the first approach that we did here was to, first of all, change kind of the way that we're generating trajectories. So before we had this hierarchical distribution. So here we still have like this hierarchical idea, but it's now being done by a diffusion model. What's nice about the diffusion model is that it has this internal process of denoising and what is it called? Yeah, diffusion. And why this is nice is because we can actually inject some guidance into that process in order to generate the kinds of motions that we care about. And the way that we chose to do this for this work is we chose to allow the user to specify formal logic for how they want a scene to evolve. And the language that we use for this is STL, or signal temporal logic. So basically, users can come up to this simulator, specify, okay, I want all vehicles to not collide. I want this vehicle to be at this position, at this velocity. I want, in this kind of formal language. And then we can use the resulting robustness formulas that this STL framework generates and use that to guide the generation process of this model. And what this allows us to do is exactly, so here's an example of, say we wanted some vehicles to stop in specific places. I'm visualizing here some of these trajectories, but basically what you can see is that in the top, I give no guidance, right? These vehicles are just moving through an intersection with some nominal speed. But in the bottom, when we ask them to stop at a specific point, you could see that they started slowing down much earlier on so that they kind of perfectly end up in that place. Now, I also understand that, from a user perspective, maybe not everyone is like a mathematician and knows how to specify STL formulas. It's not really that user-friendly. So something that we then subsequently worked on was how to make that interface a little bit more natural. And here we turn to language, and this was especially important as now we actually have such models that can interpret language. And in our case, what we did was we took like a user's language specification for how they wanted a scene to evolve, use a large language model to then output for us the kinds of logical formula that guide the scene generation, and then as per before, we use that guidance to generate a simulation. And the good thing is, this doesn't just have to come from user, you typing yourself. It actually unlocks an entire new area of data that can be used that otherwise was not able to be used for, and that's primarily textual data like police reports, insurance reports, crash reports from governmental agencies, which we can now reconstruct and then use to simulate these kinds of very rare scenarios. And I'll show you some examples of this. So for this particular case where I want to generate a vehicle that crashes into another one at a very specific, a very specific way. I want it to crash on the left side or something like that. You can see that when we pass this in, it's actually able to do this, just like that. And towards the point I was making earlier, we can take in some real-world collision reports, like from these ones are from the National Highway Traffic Safety Authority, Transportation Safety Authority, something like that. And we're able to actually reconstruct them here and use them as simulation environments, which we can then put our own vehicle in, for example. Even nicer is that these language models, they have so much inherent domain understanding of natural language input that even if we never, even if a lot of our original training regime never had the words like sparse or crowded or whatever, we're able to use these kinds of modifiers and actually have output that matches what the user wants here in terms of like sparsity for traffic. Or, beyond just generating a scene, like one-time initial scene generation, our method also enables editing an already generated scene. So let's say you do have a scene that was generated, but there's one or two things wrong with it and you want to change that. So here, you can actually continually make updates by specifying, okay, make this car do this, make this car do this, make this car do this. And one thing that I want to point out here on the very right, when we gave it the prompt to speed up cars that are moving in the same direction, in particular here, same direction with respect to this red vehicle, what you can see is compared to this one, it had to move the blue vehicle to the right, because otherwise these vehicles are turning left, which means that they're naturally going to be going slower than someone who's just going straight through. And so it actually moved this blue vehicle over. It has enough domain understanding of driving to move that blue vehicle over to then enable it to actually speed up through that intersection, which was quite interesting to see from our perspective. Now, all of this is great, but everything I showed is still at the traffic simulation level. So this is great for testing out prediction, planning, control. But remember, to fully evaluate an AV stack, we also have perception and everything that happens upstream. And so recently, when you need to model the world and actually perceive it, this is where you start entering the problems of dynamic scene representation and dynamic scene reconstruction. And so in particular, there's been a lot of recent work using neural radiance fields, or NeRFs, maybe some of you have heard this term, to reconstruct, kind of collect, environments that an autonomous vehicle has already passed through and already collected some data from, in order to, reconstruct a very realistic-looking, like data capture of this. And NeRF is able to represent that and then allow you to re-simulate what your sensors would have seen if you placed your car at a specific point and you had a specific view direction or something like that. Now, a lot of these methods, the way that they work, and maybe you'll notice in these videos, there's no moving vehicles anywhere in this video. And that's because NeRF methods typically struggle to handle dynamic objects because they break a lot of the multi-view consistency assumptions that you make within NeRF. And so what methods typically do is they'll have like an initial masking step, or maybe they'll use ground truth annotations, or maybe they'll use a pre-trained model for object detection to detect cars, pedestrians, bicyclists, whatever. get their bounding boxes, and then remove those, kind of subtract those from the scene. And actually, you can see this here if you have good eyes. You see these black splotches here on the left? Those are parked cars that were removed. But they didn't remove their shadows. I mean, difficult thing to do. But, so you can see, right? They do this first step. Then they regenerate the static world. And I mean, hey, it looks beautiful. But you are missing this dynamic element. So can we leverage this high fidelity representation capability of NeRF, but still represent dynamic objects? Because obviously for driving, this is extremely important. And more importantly, can we do this without requiring ground truth annotation or using some pre-trained, bounding box detection model, which might have some, errors or something like that? Absolutely, right? Otherwise, I wouldn't be asking these questions. And I'm going to show you first some of the results, and then I'll talk about the method. But what you can see here, so in each of these videos, this method that I'll talk about in the next slide is able to, purely from self-supervision, decompose the static and dynamic components of a scene. So what you're looking at here on the top, and I'll talk about what these colors are later, but what you're looking at on the top is basically anything that just has a normal RGB color from the sensor. This is static. This has been decomposed by our method to be static, non-changing throughout the entire scene. And then everything that has this, funky colors is some dynamic, element. So we can see that here, pedestrians are highlighted, vehicles are highlighted, and all that as they pass through. Same thing at the bottom here. We can see a similar thing where, I'm just showing you the dynamic elements of a scene without any static element, like all the static elements were removed. So the way that we do this while still using like a neural field-based approach is and this is the title actually of the paper, which will soon be online, so give it a few days. The way that we do this is we decompose every scene into 3 separate components. The first is a static field. So this is kind of like a traditional NeRF, right? I'm just modeling the static world without any dynamic objects in there. The second is a dynamic field. So whereas the first field just takes in the XYZ position of your camera and the view direction, the dynamic field, it's 4D. So it takes in the XYZ and the time, because it matters where these vehicles are in time, as well as the view direction. But now just having these 2 is not good enough. And actually, I'll show you. You guys might have noticed the difference between these 2 videos. You see in the bottom one, when the car is moving, it'll replay again. When you see when the car is moving at the beginning, do you see a lot of this artifacts around the edge? If you just do a static and dynamic field, this is what you get. Where when the car is moving, I mean, sensibly, everything in the world is moving relative to the car, and so you get these artifacts. And then when everything's stationary, everything's looking great. This is an earlier result compared to this result. To really sharpen up this dynamic understanding, this is where we also introduce a flow field. This is also a 4D field, but the whole point of the flow field is to connect the individual dynamic field objects in time. And so what the flow field is tasked with doing is calculating, okay, if we do have elements in the dynamic field, what flow or what delta should I add to them so that I know where they'll be in the next time step? And what you can do is you can use this flow field to associate your dynamic components in time, and this yields a very strong learning signal, because now you can aggregate, You can aggregate features over time, but it's also mutually reinforcing. So static dynamic decomposition is improved by also trying to learn flow. And then flow is also improved by having a better dynamic field, and et cetera. So actually, during learning, both of these are really improving the performance of the other. And what this allows you to do is, so I have here some of kind of the outputs of when you use this full model. So on the top is just the ground truth image that was passed in by the sensors. Here is the re-rendered thing. So from your guys' perspective, there's going to be no difference. You have to zoom in very, very deep to see differences. And then here, I want to point out, in this third row, we can see the decomposed static RGB. So you see this car here, gone, with no shadow remnant left behind. Because that shadow, we have first of all, we have a special head for capturing that, but also that kind of stuff is captured in the flow field. So those kinds of remnants, which otherwise you would get if you just tried to naively remove it, are actually now just naturally handled by the model. Same thing on this side. Do you see all these pedestrians? Gone, as if it was done by Photoshop. And here's the dynamic, if you just want to parse out just the dynamic objects, you can see what that looks like here. And here's the flow. I mean, it is hard to interpret, but it's basically showing you the speeds of things moving in the scene. Now, the final thing that's very impressive about this model, so not only are we trying to reconstruct, the RGB and depth and then this dynamic static stuff, we can also add additional features here. And what's quite interesting here, and some parallel lines of work that you might be aware of are, there are some very powerful visual foundation models nowadays, which are also trained from self-supervision, but they learn these very strong semantic features. So I'm showing here an example of Dino V2, which was released by Meta, I don't know how many months ago, I forget now. But these kinds of features, you can also try and train this model that I showed in the last slide to reconstruct. And what this allows you to do is generate, well, one, some very wacky colors, but two, what I'm visualizing here is those reconstructed semantic features pass through PCA just so that we can actually have some colors here. And remember, this is all, there's no labeling here or anything like that. So just by using these pre-trained features from another model, which exists for free, we can color buildings, or we can identify that buildings are buildings, they're all the same color. We can see all vehicles here, all the same color, all static vehicles here, all the same color. And I'm showing here, in RGB, I'm decomposing, the dynamic static, at least so you can see. But what's really nice about this is that now that this method that we developed originally for simulation, you can now actually use this for auto labeling. Because once you have a car pass through an environment, you can, with our approach, decompose it into dynamic static, remove the dynamic parts if you want, reconstruct these, very important semantic features, and now you can label the map, the buildings, the whatever, right? Just like this. Without human labeling, without, tons of models behind the mix. So, I know that was a lot to take in, but stepping back a little bit, I want to say in general, now is really a fantastic time for AV research. I know a lot of people say, but Waymo is driving around in SF. Yes, there's so many problems though that still need to be solved in order to really get us from 90% performance to 99.9999 performance. And one thing that's been really helpful in accelerating this kind of research in this space is that there's been a significant amount of data that's been open sourced. Ever since about 2019 or so, there's been thousands of hours of data now that researchers have access to. And it's not just from one city or this other city, or even from just the Western Hemisphere, right? We have data from all around the world. The only downside is that all of this data is kind of in a unique format. So at least when I remember doing this research, it was really annoying to, okay, I want to train something on new scenes and then test it. Okay, now I have to spend 2.5 weeks to switch my code base over entirely to a different data set and then do the exact same thing, and then hey presto, I have a paper with 2 evaluations or whatever. So to make life a little bit easier, something we've also been working on in the group is to develop a unified API for loading multiple data sets trajectory data. And at least from our perspective, this has been so, at least for us, foundational before we can even start to do a lot of other interesting research. You have to kind of build this data foundation. It's been simplifying our lives, and I know, the reason I bring it up is because we've open sourced it. It has a very open license, Apache 2.0 and all this. So if you're ever doing any research like this and you think something like this would be helpful, by all means, check it out. Feel free to, ask questions on GitHub or just email me if you have any questions. And also on the simulation side, as you can imagine, there's a ton of behind-the-scenes work that has to go into actually making this all work. And so we've also released our simulation framework for, which has that model bits and the other model. We're soon going to release that other, the language ones. We're soon going to be releasing them also in this similar framework. So if you're interested in this kind of research, by all means, take a look. Maybe it helps you. So some key takeaways here before I conclude is, or I guess to conclude, some key takeaways are whenever autonomy stack components are being designed, researched, et cetera, just keep in mind that you're never evaluating just one block. They impact downstream components. They follow other components. There are uncertainties. There are other things to take into account. So just make sure to keep that in mind. And actually, from a research perspective, revisiting the interfaces between modules is likely actually to yield more improvements, more advancements, rather than just focusing on modules themselves. Also, there's a full spectrum of architectures between classical modular approaches and end-to-end approaches. I mean, we showed one example here where we have a differentiable modular approach, but keep in mind, there's a lot of other things that can be done. So whenever you're developing these kinds of things in your robotics research or coursework, keep the idea of differentiability and task awareness in mind. And I think you'll find it can be surprisingly helpful. And lastly, closed-loop simulation is really the key enabling capability for really vastly scaling up the verification and validation of autonomous vehicle stacks. And I think really data-driven human and environment modeling is really the key that we need in order, it's kind of the key final piece that we need in order to really scale up and use this simulation for evaluation use. So with that, I want to thank you all for your attention. Please, if you have any questions or you want to see any of these papers, take a look here. We're hiring. So yeah, thank you all for your time again.
Thank you, Boris. I think we have time for one quick question, but then we can, of course, interact with the speaker outside where we have pizza. So who is the lucky person to ask the question? Go ahead.
So in the model previously, what about objects that transition from static to dynamic or dynamic to static?
Yeah, great question. So the good thing about this work is that what we do is we first take all the data from the entire traversal of a scene. So like after a car has already moved through. And because we have this flow field, if there was an object that, let's say, was like dynamic, let's say towards the end of the scene, that information makes its way back. So I wonder if I have other videos. I guess it's not this one, but I have other videos where there is a parked car that starts moving, and it's always highlighted because it brought that information back as well from the future as well when it was doing this optimization. So we had trouble with it earlier on in the project, but this flow field really helped crisp up some of that annoyance as well. It's a good question. And you can even see here. Oh, sorry, Marco. You can see here because they're all stopped. Like the pedestrians are all just standing still. So, yeah, it's there.
All right. So I think unfortunately we had to wrap up. But as I said, we're going to have pizza outside. So take that as an opportunity to ask any questions you might have for us.
Thank you.